In this video, we will use molecular orbital theory to investigate the behavior of simple homonuclear diatomic molecules. Homonuclear means that the two atoms that are coming together to form the diatomic are of the same element. Let's now look at the first two elements on the second period or second row of the periodic table and look to see what molecular orbital theory predicts in terms of the bonding in the diatomic molecules. The first one is lithium. So lithium, the way we would set up our molecular orbital theory diagram is we start by having our two atomic orbitals, one for each one of the lithium atoms that will be combining together to make the diatomic lithium. So we have a 2s orbital from one lithium and a 2s orbital from the other lithium, both of which have one electron in them. When they combined, through constructive interference, we get a bonding orbital which is lower in energy than the initial energy of the orbitals that they started out in, and we get an antibonding orbital through destructive interference, which is higher in energy than the energy of the two orbitals that we started with. Because we have one electron in each one of our two orbitals, we then would place two electrons in our set of molecular orbitals. The two electrons, following Hund's rule, Aufbau, and the Pauli exclusion principle, would both be put in our lowest energy state with two electrons in that orbital. For the calculation of bond order, which is 1/2 the number of bonding electrons minus the antibonding electrons, we would take 2 minus 0, which is 2, 1/2 of that is 1, and so we would predict that our lithium diatomic would be a stable molecule that has a bond order of 1. For beryllium, looking to see will it form a diatomic molecule, we take our two atomic orbitals, which in this case for beryllium would be 2s orbitals, both of which have two electrons in them. We combine them together through constructive and destructive interference to get two molecular orbitals. Because our original atomic orbitals each had two electrons in them, we have a total of 4 electrons to place. We would put 2 in our bonding orbitals, which fills it up, and then 2 would go in our antibonding orbitals. Calculating out the bond order would be 2 from our bonding minus 2 from our antibonding, which gives 0. Divided by 2 is 0. So the bond order for a beryllium diatomic molecule would be 0, meaning that it is not a stable diatomic and will not form. Up until now, we've been looking to see how our s orbitals will combine together to give molecular orbitals. Now let's look at what would happen for p orbitals. We have two different options for our p orbitals interacting. They can either interact directly along the internuclear axes, which would form a sigma bond, and as we will see later, we could have them interacting perpendicular to the interatomic axes via a pi bond. So first, the sigma bond. If we have two sets of 2px atomic orbitals combining together along the x-axis, we can either have constructive interference, where the area where they're overlapping adds together, giving us a sigma bond here, or we could have the two adding together via destructive interference. If we're adding them together via destructive interference, then wherever they overlap, they will destructively add, meaning that they will cancel each other out. This leads to having a node between the two nuclei and leads to antibonding. The resulting orbital would look something like this, where you have small parts of orbitals on the inner part of the internuclear axes and a node, a region of space where there is 0 probability of finding your electron directly between the two nuclei. So this is your antibonding orbital that results from a sigma bond involving two p orbitals. We can also have p orbitals interacting that are perpendicular to the internuclear axes, meaning that you have your two nuclei here. The internuclear axis is aligned directly between the two nuclei. So if we take the x-axis as being our bonding axes, then the pz are going to be directly perpendicular to the axes along which you would have your regular bond. Similarly, the py would also be perpendicular to the axes. The way that we can have them overlap would be through either constructive or destructive interference. If they constructively interfere, then where you have the lobes and they overlap, they will get larger. So through constructive interference, you would get a bonding orbital that looks something like this. You have a node in between, but that is where the node already existed in the pz orbitals. For the antibonding orbitals, the two pz would be adding together through destructive interference, which you can sort of think of as taking your first pz and subtracting your second. The result is wherever the two overlap, they will destructively interfere. They will cancel each other out. So what you will see is the region where the pz orbitals should overlap, you will get a node where there is zero probability of finding the electron. This results in an antibonding orbital that would look something like this. Note that the symbols for our pi bonds, or the overlapping of two sets of p orbitals, would be pi for our bonding and pi star for our antibonding. For the py orbitals, they look the exact same as the pz. The only difference is that instead of lying along the z-axis, they are lying along the y-axis. When we look at elements that have electrons in both their s and p orbitals, we need to come up with molecular orbitals that account for all the different orbitals that are overlapping. Previously, we had been talking about things only having s orbitals. So this part down here is what you should be familiar with already from our previous examples. When we try to include our p orbitals, we need to look at how they can overlap. You could have two sets of pi bonds through the p orbitals that are perpendicular to the internuclear axes, and one sigma bond coming from the orbitals that lie directly along the axes. You also have your pi antibonding and your sigma antibonding that are associated with the destructive interference. Now there is a slight difference between the molecular orbital diagrams for our boron, carbon, and nitrogen as compared with oxygen, fluorine, and neon. The difference being the ordering of our sigma and pi bonding orbitals. For boron, carbon, and nitrogen, the pi orbitals are lower in energy than the sigma, whereas for oxygen, fluorine, and neon, the sigma bond that's involving the p orbitals is lower in energy than the pi bonds. Looking to see how we would fill one of these out, let's look at the examples of carbon on the left-hand side and oxygen on the right. So first thing we would do is fill in our atomic orbital diagrams with the number of electrons coming from each. So for carbon, we have 4 valence electrons. So we would fill first our 2 sets of s, and then 1, 2 for our p orbitals. Then for the other one, then for the other carbon, we would have our 2 electrons in our s orbitals and then 2 in our p orbitals. Right? This is the exact same drawing for electron configurations that we did earlier, in earlier videos. We then fill our molecular orbitals with the number of electrons from the orbitals that we're combining together to give our molecular orbitals. So for our s orbitals, down at the bottom, we have a total of 4 electrons, 2 from each one of our s orbitals. So then we have 4 electrons that we need to place. So this would be 1, 2, 3, 4. Okay. To do the next one, we would take the 4 electrons that are in our 2 sets of p orbitals. 2 from the p orbitals that are in the left carbon and 2 from the p orbitals that are in the right carbon. Putting them together, we have a total of 4 electrons to place. So we would do 1, 2, 3, 4. The bond order for this would be, our bond order is equal to 1/2 times the number of bonding electrons minus the number of anti-bonding electrons, which would be equal to 1/2 of our total number of bonding electrons. We have 2, 4, 6 from these orbitals. So we have 6 sets of bonding electrons minus we have 2 anti-bonding electrons. So 6 minus 2 is 4. 1/2 of 4 is 2. So what we would expect from carbon is to have a bond order of 2. For oxygen, let's look to see what we have. For oxygen, the electron diagram would be 2 sets of S. Oxygen has 6 valence electrons. So we would have this for our configuration on the left one. On the right, we also have oxygen, so it will be the exact same. Now, combining them together in our sigma bonds from our s orbitals, we would have 1, 2, 3, 4. For our p orbitals, we have a total of 8 electrons that we need to place. 1, 2, 3, 4, 5, 6, 7, 8. So our bond order, which again is 1/2 the bonding electrons minus the anti-bonding electrons, our bond order would be equal to 1/2 of our total number of bonding electrons are 2 from here, 4, 6, 8, minus we have 2 here in our first anti-bonding orbital, and then we have 2 that are occupying our pi bond. Then we have 2 that are occupying our pi anti-bonding. So that's a total of 4. 8 minus 4 is 4. 1/2 of 4 is 2. So our bond order from oxygen, we would expect it to be 2. Now there's an interesting thing that occurs for our oxygen. We have up here 2 electrons that are in anti-bonding orbitals, but they are electrons that are by themselves, which means from this we should have something that is paramagnetic. So because we have these unpaired electrons, this will interact with a magnetic field. This is what it looks like when we fill out all of our molecular orbital diagrams. As we saw for carbon and oxygen, both of them have a bond order of 2. For boron and fluorine, they both have a bond order of 1, and then nitrogen would have a bond order of 3. In each case, it's the number of bonding electrons minus the number of anti-bonding electrons, quantity divided by 2. We can take a look to see at what our bond energies are going to be and compare what is predicted by carbon versus oxygen. For carbon, the bond energy, the amount of energy that it would take to break apart the diatomic, is 620 kilojoules per mole versus oxygen, which is 498 kilojoules per mole. The reason why, according to our molecular orbital theory, that the bond energy for carbon is greater than that for oxygen is because carbon has all of its electrons that are making up its bonding in a lower energy set of molecular orbitals, whereas for oxygen, that is counterbalanced by having these anti-bonding electrons, which will cancel out some of the favorability of having them in this higher energy orbital. So the net result is that oxygen has a weaker or lower bond energy than does carbon. This is why oxygen is more reactive than carbon. For neon, the bond order is 0. This predicts that neon will not form a diatomic, which is consistent with our noble gases. Noble gases do not form diatomic molecules. We can see this from our molecular orbital theory, where all of our bonding orbitals are counterbalanced by the antibonding orbitals. So we have down here in our sigmas that are coming from the s's, we have 2 electrons in bonding, and we have 2 that are in the sigma antibonding. We have 2 that are in this sigma bonding coming from p orbitals. Those are counterbalanced by our sigma antibonding coming from the p orbitals. Similarly, our 2 sets of pi bonds are counterbalanced by 2 sets of pi antibonds. So our molecular orbital theory is able to make lots of predictions that valence bond theory was not able to, including that oxygen and boron as diatomics should interact with a magnetic field, meaning that they will be paramagnetic, which was one of the things that we were trying to explain and one of the reasons why we are moving towards molecular orbital theory. This also predicts that carbon, nitrogen, fluorine diatomics will be diamagnetic. They will not interact with a magnetic field, and it also predicts that neon will not form a diatomic molecule, which is what we see experimentally.